Excited to tell it to you at the hangout yesterday, and then you left, so I had to hold it in all day.
Right, so I'm setting up the live.
Oh, God.
All right. I'm going to copy the link of the live stream. Okay, I saw a new subscriber.
Yeah.
So if you haven't subscribed, make sure you subscribe our channel. Hello.
Hello. Hi. Oh, hey. You've sort of seen this presentation before, but
Oh, is it the same?
no, it's different, but there are some slides copied.
Okay, so we have like two experimentalists.
I'm curious.
What's your name?
Jeet.
Oh,
Jeet Shah.
okay. Right. Yeah, I thought you were Subra, or maybe I was mistaken.
I'm still the only equalizing factor.
Okay. So the third journal club talk live streaming. Right. So hello everyone. Thank you everyone for showing up for our third journal club talk. Today we are welcoming Mr. Mike Winer, who's a student in the physics department and a student of Brian Schwingle and Victor Galisti. So Mike has done some work in the SYK model and which is the intersection of hydrogen physics and condensed matter theory. And today, fortunately, we will have Mike to talk about the newly to talk about the spin glass, which was just awarded Nobel Prize. Let's welcome Mike.
Thank you. That's probably the kindest introduction I've ever had. Proves you don't know me very well. Okay, so I'm going to be talking about spin glass. Is there like a button I can use to control this?
Yeah, you have to. You can go to the screen and use the keyboard.
Okay. Let's talk about spin glass. So spin glasses, there's two things that are really important about them, and these two phenomena are totally different. You can have one and not the other, but they both get lumped under the same name, and there is a connection between them, which we might get to. So first then is ergodicity breaking from kinematic constraints. I'll talk more about that later, but the basic idea is you have some, space of configurations, right? Like, and you have trouble exploring all that space of configuration. So the simplest example of that happening is like, you have two wells and a ball is trapped in one of them. It's never going to explore to see if the other well is lower, right? That's we're all familiar with it. And when that happens in a condensed matter system, it's called a spin glass. The other is replica symmetry breaking, which is a pretty complicated and technical thing, and I'm not going to go into it in detail. But the basic idea is, a lot of the time when studying disordered systems, we make an approximation called the annealed average, or the annealed approximation, and sometimes that breaks down. When that happens, that's often associated with ergodicity breaking, so we put them under the umbrella term of spin glass, even though they are separate things, and again, you can have one but not the other.
Okay, Mike, before you proceed, can you simply describe what is a spin glass? Like phenomenology.
Okay, so my favorite example of the spin glass, which is, this is like a toy model here, is just you have some incredibly complicated energy landscape, and this is true for lots of physical systems with complicated interactions. This is also true in lots of, like not quite physicsy computer science applications that physicists like to talk about to get money. Right, so you have some incredibly complicated energy landscape with lots of local minima. And as we all know in thermodynamics, systems try to find minima of energy, or to be more precise, minima of free energy, and sit there. And a spin glass, can be some system, like I'm gonna have some cartoon pretty soon. Let me draw the cartoon. And I distinctly remember last time I drew the cartoon was horribly counterproductive. So maybe we're gonna be in trouble, but we'll see. The cartoon I like to draw is, woo, woo. Okay, this is some energy landscape. Obviously, a real complicated system is going to have more than one coordinate. So just imagine that I drew this in 12 dimensions instead of one. And if the system ever gets stuck here, it's gonna think it's doing pretty well. It's just gonna stay there, be like, I've relaxed toward an equilibrium. And it's not gonna notice that there might be a deeper equilibrium here and an even deeper equilibrium over here in 12-dimensional space and so on. So that's ergodicity breaking, and that's the baby example of a spin glass. So if we were to go and do our thermodynamics and be like, the probability distribution, like this system will never reach a thermodynamic equilibrium. If we drop the particle here, it'll never reach the Gibbs Maxwell-y state where most of the probabilities over here and some of it's over here and tiny bits over here. It'll just always stay here. It won't.
So are you talking about classical system or quantum system?
So for now, let's imagine it's classical coupled to a heat bath. Quantum is going to be more or less the same story, but we're not going to do any quantum today.
But if it was quantum, then if you wait for a sufficiently long time, then maybe it would go to.
Yeah, so there would indeed be a tunneling time for quantum. You find that the tunneling time is going to be exponential in the height of this, right? Which could be really, really long, longer than the universe. And then actually, you can find for a lot of realistic systems, it wouldn't tunnel. So, like if there's some time called the Heisenberg time, which is the inverse level spacing. And if the time to get from here to here is longer than the distance between, than the time between energy levels, then it just can't tunnel, and all of the energy eigenstates are localized here, here, here. If you drop it here, it will literally never, not ever tunnelize. So yeah, depending on and Chris Baldwin, who works here, made a big, justifiably made a big deal about there is a distinction between things that take an exponentially long time to tunnel and things that take an infinite amount, like literally never tunnel. And there is indeed a phase transition there, which is often underappreciated by people who don't know Chris.
Okay, Mike. So a quick question before you proceed. According to my impression, there are lots of phenomena that corresponds to ergodicity breaking, like the many-body localized states or et cetera, et cetera. So what is the definition, the true definition of a spin glass?
I don't know the true definition of a spin glass. It's a bundle of similar but unrelated phenomena, but distinct phenomena. I don't think there is a true definition of a spin glass.
Okay. And how is
so what distinguishes this though from MBL systems and Anderson localized systems and integrable systems and all that is the system is chaotic, right? Like the system will not fully thermalize, but it will reach a thermal equilibrium in the area around as well. The system I drew is one-dimensional, so it won't. It's also integrable, but like in general, it'll thermalize to a point, which MBL systems won't. But it will not thermalize fully. So it is distinct from an Anderson localized system or something like that.
okay? What about this spin liquid?
Spin liquid, as far as I know, it's totally unrelated. I've heard about some new paper that talks about a connection between them, but I think it's a different thing.
It's a different thing. Okay.
Yeah.
All right. Any more questions?
Could you write out Hamiltonian perspective?
I will later. So I'll write the one that just won a Nobel Prize. So we have a bunch of spins, right? For now, spin up, spin down. We're not going to worry about anything more complicated than that. H equals sum over I comma j, j sub I j, sigma zi sigma zj. People see that? People see it? Okay. So this is an ensemble of Hamiltonians that depends on the j's. if we randomly select the J's from a Gaussian distribution, so all-to-all two-body interactions, J is discovered, J chosen independently identical distribution. Then this is called the Sherrington-Kirkpatrick model, which was solved by obscure physicist Giorgio Parisi, who just won the Nobel Prize. And this exhibits ergodicity breaking and replica symmetry breaking. In fact, it exhibits some beautiful full replica symmetry breaking that we are not remotely going to get into. And this is a nice example of a spin glass. So you're going to find there are, if you try to, there's obviously 2 to the n configurations where n is the number of spins, and there are going to be lots of low-lying configurations that are nowhere near each other. So this is a good example of a spin glass.
Okay. Any more questions, especially experimentalists?
Okay. Let's see. Okay, this is I guess the same cartoon of the energy lens. This is a lot of the same stuff I was talking about already. So yeah, how do we have ergodicity breaking? Like I said, the way we do it, to be simplest for me to visualize way to do it, is to have a complicated energy landscape and then high barriers between the minima. There's also something like this is a structural glass, like the glass here. It's not, as you can think of it as an energy barrier, but you can also just sort of have like a small region of phase space connecting to, or even non-zero, a zero region of phase space connecting the two components. So suppose we have, and this is, people say, oh, glass is a slow moving liquid, and then people say, no, it's not, and then people start arguing. This is what they're talking about. So imagine, we have some, liquid or a bunch of disks that are hard disks bouncing against each other, and really, we only understand this in infinite dimension, blah blah blah. But I can't draw infinite dimensions. I think that's a slightly higher art skill level than I have. So like, but if the disks are packed tightly enough, like, whoop, and let's say the diameter of the disk is more than half the size of the flask for now, right? Obviously, this is true in the thermodynamic one where the system is infinitely large, one disks are dense enough. But for now, let's just go ahead and say the diameter of the disk is more than half the width of the system. Then there is a kinematic constraint that stops these two from switching places, right? They will never switch places. Now, you can think of it as an energy constraint if you want by saying, oh, the hard shell potential, but I think of it as a phase space constraint, keeping them from making this jump. That's a similar thing where, it can't explore all of the phase space that it wants to explore. So yeah, those are the 2 standard ways you can have a energy barrier, or you can have a, it's very, so, and then the thermodynamic limit, of course, you can always imagine that, these guys want to switch, every other nearby disk goes away with some finite probability, and then they switch. But that's very, very unlikely, right? So in the thermodynamic limit, you can always switch the 2 disks you want to switch, but you can't switch. It's very unlikely. So it's a small region of phase space. It takes an exponentially long time.
I don't understand why there's a phase transition between exponentially long time and the infinite.
Between exponential and infinite?
Yes.
So that's a quantum phenomenon. That's purely
How can it be used to
okay, so for now, let's just, this isn't even really a, this doesn't require anything too complicated. Let's just imagine we have 2 harmonic oscillators. Okay, 2 harmonic oscillators and some really, really, really weak amplitude to jump between them. And they have like incommensurate frequencies and all that, right? So one of them is, or actually, let's do even better. So one of them has energies, E1 plus n omega, and the other has E2 plus n omega, where E1 minus E2 is not a multiple of omega, right? Whereas the energy spacing for this system is omega, and you can be in either of these 2 wells. And let's say that there's a a weak term in the Hamiltonian for tunneling between them. Okay? So H equals H1 tensor sum H2, right? So it's a tensor sum, right? These are not, the system can be either the first well or the second well, right? Plus some H tunneling. If we view this as a perturbation, then we can, and if the magnitude of H tunneling is really small, we can say, so we start with an eigenstate, which is like, the 6th excited state here, and then we do perturbation theory, this is a perturbation. And if the magnitude of H tunneling is really, really small, then almost all of the amplitude is just going to be stuck in the first well, right? Because the perturbation, if perturbation is much, much smaller than the energy spacing, then the series converges, and it converges with not that much change. So that's how you can have it, so that if the amplitude for jump, if the term in the Hamiltonian for jumping is small enough, then the eigenstates are all localized. If the eigenstates are all localized, you will literally never jump. I mean, there will be some non-zero probability for jumping, but there's no amount of time after which it will be 50%, right? Or no amount of time after which it will be 10%, right? It will always be really, really small probability of jumping. That's the.
But this is still exponential.
What do you mean?
Exponential relative to the energy difference between the coupling energy and the band gap.
Sorry, what are you saying?
So you have the coupling, which has some key, and you have some band gap that you need to cross.
Yeah.
And the probability is still proportional to the exponential, the ratio
The exponential of what ratio?
of the ratio of t over the band gap.
Sorry, you think the probability is exponential in time? Is that what you're saying?
Yeah.
I definitely don't see why that would be true. Yeah, I feel like the probability is certainly going to be bounded, and because these states are pretty localized in, say, the first well, it's going to be bounded pretty low. Is what I'm trying to say. So that's how I've taken it, and that's how you have it, so it'll never transfer. Am I communicating? Do people understand what I'm trying to say? I'm going to be honest. I do not fully understand what I do not think I fully understand what you're saying.
I still don't understand why there's a phase transition between exponential. Could you give an example like exponential tunneling and this example and see like clearly why there's a phase transition between?
Okay, so I do not have an example I can work out on the board.
Okay.
No, yeah, I don't.
Yeah, or I can translate Yujuan's question to another question.
Okay.
If there is a spin glass state, then what states can be transformed into that state? And what happens during the phase transition?
So what, like, you're asking about like sort of the thermodynamic phase transition from non-glassy to glassy?
Correct.
Okay, so yeah, this is related to there being some slightly different definitions of spin glass. So if we use the ergodicity breaking thing, then actually there isn't what I'll call a bump. Like there's no the free energy doesn't have any discontinuity or higher order discontinuity when we break ergodicity. It does have these crazy things when we look at the what's it called replica symmetry breaking transition, which I might get to later. But the ergodicity phase transition is a dynamical thing which does not have an obvious signature in thermodynamics that I know of.
I see. What about like quantum phase transition instead of thermodynamic phase transition?
So we're looking at for temperature things.
Yeah.
Okay, so first of all, I don't know what I'm talking about when it comes to this. But let me try to say things anyway. Okay, so I'm trying to think what a quantum phase transition for a spin glass would look like. So what we hit. Okay, I don't know. I know a small enough amount about quantum phase.
Yeah, I know there's a paper by David Pecker, was probably his most famous paper. That's about some glass transition. I think I'll send it later in the slide.
Okay, so now I'm gonna try to, oh God, you can't see the titles of my slides, can you? Okay, this slide is called The Spirit of Tap States or something like that. So I'm gonna try to explain what a tap state is. And I have spent a huge amount of my life arguing with people about what a tap state is. So bear in mind, you're only hearing the correct point of view and not all the incorrect points of view out there. But I'm gonna tell you how I think of tap states. And it might have changed the slide. Okay, so if we have the complicated energy landscape that I showed you before, then there's some Boltzmann distribution. You can always define the Boltzmann distribution, right? E to the minus beta h is always a well-defined distribution. I guess there are some systems where it's not normalized. We're not thinking about that, right? There's always some Boltzmann distribution, but it can be complicated and unrealistic, and we never reach it. So I like to think of tap states as simpler approximations to the Boltzmann distribution.
What's the tap state short for?
Thouless Anderson Polymer. Yeah, very famous Thouless, very famous Anderson, and I'm sure some people have heard of Polymer.
Okay, yeah, can you give some definitions or just assume everyone? No,
of what a tap state is. I'm going to try to give you the gist. No one can agree on a definition. I'm sorry, spin glasses are a very the field is not in equilibrium, you might say. We do not agree on definitions about anything. That's one of several reasons why this thing is complicated. We don't agree on definitions.
Why are you introducing this?
Why am I introducing the concept of a tap state?
Yeah.
So I think it's a useful concept. And it's so it's definitely going to be necessary if you want to understand replica symmetry breaking. And I think it's important if you want to understand ergodicity breaking too. So the tap states are like good approximations to the Gibbs distribution, or at least like low distributions that can't be locally improved upon. So you can go ahead and you can show that basically the natural forms of tap states are you take some minimum of the potential, right? Which we'll call x naught. And it's just going to be e to the minus beta h. X is near x naught, 0 otherwise. So for a reasonably broad definition of near, for instance, we can say nearer to x naught than any other local minima. So what's going to happen is near x naught. This is pretty substantial. As you get further and further away, this probability gets smaller and smaller. And then eventually we're going to force it to 0, but by that point it's so small that who cares what we're doing to the probability distribution. It's basically continuous because we're forcing it from infinitesimal to 0. And by definition, there are places, and we know that this is going to happen, that it's negligible when you're far from local minima, because if there was like a path from one minimum to another, where along the whole way, e to the minus beta h was large, then it would be easy to get from one local minimum to another. So ergodicity breaking is why we're allowed to have tap states. Ergodicity breaking is why we can say, hey, look, we can just expand the energy around this one local minimum, and then there's no substantial amount of probability mass far from any local minima in sort of the border zones.
Good question.
Sure.
If you believe in ETH, which I personally don't believe, what will the tap state look like in terms of ETH?
Okay, so again, so ETH is about eigenstates. Eigenstates are really, really long time quantities. So ETH is the eigenstate thermalization hypothesis. So what the ETH says basically is if you take an energy eigenstate and of a many-body system and calculate any sort of few-body expectation value, it'll look like the thermal expectation value. And I guess this is related to this this infinite time versus finite time distinction I was making earlier, right? So for some spin glasses, we have ergodicity breaking. But the ergodicity breaking is true for exponentially long time scales, not infinite time scales. So the eigenstates, like if you want to get to an energy eigenstate, you need to sit around for a very long time, right? Longer than the energy gap between nearby eigenstates. And for some systems, that means the system has thermalized by then, and the spin glass behavior is sort of gone after you've waited this insanely large amount of time. And then, as Chris Baldwin would point out, for other systems, even once we've waited for the ETH time, even after we've waited the Heisenberg time, picked out a single eigenstate, it still hasn't thermalized. So in that version, I guess you could really say ETH does not apply to those spin glasses, because in those spin glasses, the eigenstates are going to be localized in one tap state. Whereas in spin glasses with merely exponentially long times, the eigenstates, which again the eigenstates are an incredibly long time object. The eigenstates are going to be delocalized. So spin glass, lasts exponentially long time, but it might not last infinite time.
Okay.
And eigenstates are inherently a very long time phenomenon. I think people don't appreciate that enough. But if you want to ask anything about an eigenstate, you're asking about something that can only be measured after a really long time, unless you're making some sort of approximation, assuming something.
Okay.
Okay. So tap state, is again, so is the idea, it's the thermodynamic distribution, or if we're doing quantum stuff, it's the density matrix that you get when you try to minimize Gibbs free energy, near, while trying to maintain not quite unimodal, but any small number of modes and having a sort of connected probability distribution. And I don't have I understand it's a little bit of a froofy, weak definition. I want you to know I put a lot of work into that definition, and it's not going to get any better in the time available. It's just hard to come up with a really tight definition of this.
So with this near definition, if you have a bunch of minima close together, you're going to have a smaller tap state, right? Smaller width of the tap state.
So if you have a bunch of minima close together, then first of all, there's the question of is it possible to jump from one minimum to another? Right. So in that you can have the answer to yes or no, right? Depending on how high the well is between them. So if you have a bunch of minima close to each other, but it's still impossible to jump between them, then yes, these tap states will be super narrow. You can imagine a system which is, this is an unusual Hamiltonian, but whatever. You can imagine something like, right, where it can jump between these minima. And they're, in a certain rigorous sense, this is extremely unlikely to have happen in the thermodynamic limit, but whatever. If you have this, then okay, did all the things where I said local minima, count this as one local minimum, and the tap state would be delocalized throughout this whole region. That's a good clarification point. Any other questions? Yep.
So in these tap states are isolated, right? So is there any meaning to the total partition function that is the sum of these tap states if you can only be in one specific state of time? I mean, if you're using the partition function to sum over, the possible states to derive some thermodynamic value, or observable, does that have any meaning if the state's only in a particular well?
So not much is the
Okay.
answer, right? Yeah, so that's a good point. And that's one of the main points is once we've broken ergodicity, the state is stuck in some well, then like, all the other contributions to the partition function don't really matter. And this is a huge deal for thermodynamics, right? It means everything you heard in your first thermo class was a lie, and you should demand a refund. Right, and you should go and replace all of those, all the free energies with the tap free energy, which is just when you take the partition function within this subregion. There are a few quantities where it will be the same either way you calculate it, but in general, no, the partition function loses a huge amount of its zing once we break ergodicity. It loses a huge amount of its value. I don't honestly say its main values, it's often easier to calculate. And sometimes you can still get the right answer using it, but it's lost most of its value.
How do you quantify that? How do you quantify the value that's been lost?
I mean, so again, so like, what do we like to do with partition functions? And the first thing we do with partition functions, of course, is normalize the probability distribution.
Yes.
And we would not get the correct normalization if we used the full partition function, right? I guess I raised the tap thing, but the thing we're using to normalize the tap probability distribution is not the partition function, right? It's it's integral within the smaller region of either minus beta, not integral over all of its space. So we don't use the full partition function. We
I
use
see what you mean.
the tap partition.
Yeah, so you're saying that the reason why we don't use the total partition function is because the phase space inherently is limited by
Yeah, exactly.
by the constraints. Okay.
So the partition function is a full phase space quantity, and we now want to replace it with a region of phase space we're in. So we call it the tap. I guess I'll use the phrase Z tap here, but yeah, we want to use Z tap and F tap and every other thermodynamic potential sub tap for just this one region. This is just a bunch of facts about tap states that are that I find cool. You're not going to remember all of them, but who cares? So there's so the actual glasses that appear in the real world are really, really hard to study, and no one knows if these facts are true about this glass, but these facts are all true about the mean field all-to-all interacting spin glasses that we can actually understand or begin to understand. So these systems have exponentially many minima of free energy, exponentially small overlap between the tap states. The system is ergodic within one tap region, sort of arguably by definition. Likewise, you can't jump between them. And if it's ergodic within the tap region. If we let it thermalize within a tap region, it will reach the tap distribution, right? So what we can almost do is just say, we're cutting our phase space down to the region around the local minimum, and then we're allowed to do normal thermodynamics, right? That's sort of the ergodicity breaking story here. Okay, so now this is about quenched versus annealed. The slides is quenched versus annealed. So I'm going to be honest, it takes like 4 tries before you understand the distinction between quenched and annealed. So I assume for most of you, this is try number 1. But we're going to make it as valuable as 2 tries. Quenched versus annealed quantities are things we calculate about a disordered system. So these averages here are all disorder averages. So like if we had the Schrödinger-Kirkpatrick model, we'd be averaging over all the J's, right? And so in quenched, this is the disorder average of the thermodynamic average of a quantity, right? That's what the quenched average is. And 99% of the time, that's what we mean when we say the average value of a quantity, right? The annealed quantity is a little bit different, right? He's sort of moved around where the averaging goes here. And the annealed quantity is 99% of the time not what we want, but it's easier to calculate. So whenever we possibly can, we just calculate the yield and say it's the quench thing and get away with it, hopefully get away with it. So if you've ever worked with the SYK model, every average we calculate for the SYK model just about is an annealed average. And what we're interested in is the quenched average, and we always get away with it with the SYK.
So what does annealed average mean? I mean, shouldn't you take log the average of physical quantity, which is log C?
Yeah, so the annealed average, that's correct, is not a physical thing we can measure usually. So the origin of these terms has to do with, when you're actually fiddling around with a metal or a glass or something. So a quenched average is like, oh, the system is at some, in some high energy state, and the couplings are determined randomly, and then we like throw it in water really, really fast, and the couplings get frozen where they are without any respect to anything. Right? So the couplings are just random. And you can think of the annealed average in a way as weighting the there are different couplings, and some of the couplings allow the system to have lower energy ground states than others do, right? And in an annealed average, those couplings are going to contribute more to the overall answer here.
So, Mike, let me ask a quick question. So, in terms of the quenched average and the annealed average, can you draw the energy landscape again and tell us over whichever landscapes are the quantity being averaged in terms of quenched or annealed?
So these are both disorder averages. So I need to draw not just one energy landscape, but an ensemble of energy landscapes.
Yeah.
So I might draw an ensemble of size 2. How about that? Yeah, okay, that might work. And I'm for now going to draw one local minimum. I don't know, whatever. We'll see what happens. This is one landscape, and then this can be the other landscape. Okay, this one is much deeper. So actually that's a horrible example. I take it back. Okay. And suppose our distribution over landscapes is each of those landscapes is going to come up with probability 50%, right? Obviously, this is not at all a realistic example, but this is hopefully an example to understand where we're randomly choosing a Hamiltonian and then doing thermodynamics on that Hamiltonian, which is fundamentally what we're talking about here. So if we want the annealed probability that it's in okay, first, what is the quenched probability that it's in roughly this region? Can someone try to work through that? Okay, well, it's really only going to be in this region if we pick this Hamiltonian, right? And so, and then if we pick this Hamiltonian, it's roughly 50-50 between these two regions, right? Okay, so it's 50% of 50% is, come on.
25.
Okay, so the quenched probability of being over here is 25%. Okay, but let's look now at the annealed average. So with the annealed average, what we're doing is summing over all Hamiltonians of e to the minus beta h, then we're going to divide by the number of Hamiltonians, right? So we can be like, what is integral dx of e to the minus beta v1 plus e to the minus beta v2 times whatever our quantity we're interested in is, divided by integral dx e to the minus beta v1 plus e to the minus beta v2. People understand how that's the annealed average?
It's a little bit too. The color is
Sorry.
not clear. We can use the red one.
Sure. Going forward, I'll use the red one. Okay. But the basic idea is, since this well is so much deeper, it's going to dominate the annealed average. Right? Because it's the annealed average, we're giving preference to deeper wells. And so one way to think about this is the annealed average gives a huge amount of preference toward Hamiltonians with really low ground states. Whereas the quenched average, every Hamiltonian contributes equally. And usually when we take a disordered system, like it is sometimes the annealed average is what you want. Like annealing is an actual thing that happens in the real world where the annealed average is relevant because you're choosing a ham. Like, but usually what we're more interested in is the quenched average. But the annealed average is easier to calculate, so we just fudge it and it often works. Okay, so do people understand the distinction between quenched and annealed averages at least a little bit? Okay. Okay. Okay, is there some way we can like get rid of this?
Oh, yeah.
There we go. Okay, physicists. Okay. So yeah, the random energy model is the simplest possible model of a spin glass. So we have 2 to the n microstates. It's a classical model with 2 to the n microstates, and the energies of these microstates are chosen independently at random. It is not a realistic model of anything in the real world, but it is it is also very, very easy to do math on. And it is a great example of a spin glass. So do people understand the random energy model? Yeah.
So this is a little bit more complicated than just having n states that are independent with random energies, because each microstate has a random energy instead of each. So I see 2n and I think of like a chain of occupied states or unoccupied states. That's not this.
So you can view it as a chain. There's no physical structure, right? So usually when you have a chain, there's some.
Yeah. But here, I mean, each microstate has an energy, not each site.
Yeah. So depending on how you look at it, this is different, from a world where you have a bunch of independent sites, which is what you might think.
It's like independent sites and totally random interactions.
Yeah. So you can think of this as like like the n, where there's like an nth order interaction, so you can just single out a single microstate.
Okay.
So yeah, very unrealistic, but great for doing math on. So let's calculate the partition function. It's just going to be Gaussian integral. Okay, and quick question. Would we be interested in this for I want to know if any of you remember which one's quenched and which one's annealed. But is this going to be useful for getting quenched averages or annealed averages? I am so impressed that you got that. I was only like 75% sure. Yeah, this is the disorder average of partition function, which is fairly easy to get, right? Like, we're summing over 2 to the n terms. Each of these terms is just a Gaussian integral. Boom, boom, boom. So that's not hard. That's something we can all do, hopefully. And we get our the disorder average of z. Whereas getting the disorder average of log z, does anyone have any idea for how you do that? Okay, the best way to do that is assume that we can just call the log of the disorder average of z and hope that works, which, by fact, it doesn't. Okay. So I also want you to notice there's no phase, like, an expected value of z is purely analytic here, right? So there's no, if you think phase transitions come from the absolute value of z, or the expected value of z, then there's no phase transition, right? There's no discontinuity or anything like that in the annealed free energy, right? Yeah. Okay. So I'm going to use a baby example of the replica check. I don't think we're ever going to do the full. What times, by the way? I don't know if I'm doing it. Okay, yeah. We're not going to have time to do the full replica trick, but I'm going to hopefully convince you that there's stuff going on here, that there's room for non-triviality. We're supposed to want the expected value of z squared. Then we can do that by saying we have two copies of the system. And each of those copies is in a microstate. So how many total microstates are there for the doubled system? Somebody? Yeah.
4 to the power n.
4 to the n, yes. We have two copies of the system, each with 2 to the n states, and multiply that together, and it's 4 to the n microstates of the doubled system. And so the expected value of z squared is just the expected value of z of the doubled system, right? That's what we calculate here. And there's two possibilities. Either sigma 1 equals sigma 2 or it doesn't. So sigma 1 does not equal sigma 2, then we get this first term here, right? Summing over the many, many, many possibilities where that's true. And then it's much less likely that sigma 1 is, there are much fewer terms where sigma 1 equals sigma 2, but we get an enhanced contribution. Basically sort of because there's like a constructive interference between these two terms. Do people see this? Can they draw that calculation stuff in their head? Do you want me to work it out?
I trust you.
You should. Thank you, it means a lot. I should at least make it so you can see the answer instead of
Yes.
seeing me. Okay. So z squared, there's a phase transition in terms of which of these two terms dominates, which happens right here. Right? Like if beta equals 0, this term is much, much bigger. This term is 4 to the n, this term is 2 to the n. And at huge beta, this term is way bigger than this term. So the second term dominates, right? Because the thing in the exponent is much bigger. And here's where the transition happens. So, okay, that's crazy. There is no phase transition if we look at the expected value of z, but there is a phase transition if we look at the expected value of z squared.
Wait a second. So how do we define a phase transition here?
I would say
Discontinuity of
a
what?
phase transition is where the log of the partition function divided by n isn't analytic.
Okay, yeah, that makes sense, yes.
Okay, so of course, what we're really interested in is not the expected value of z squared, it's the expected value of log z. And the expected value of log z is equal to the limit as epsilon goes to 0 of what is it? Z to the epsilon minus 1 over epsilon, is that right? I'm gonna assume that morally this is right.
Is that like log approximation?
Yeah, I mean, yeah, this is just you can get this by Taylor expanding epsilon or L'Hopital's rule or something. In fact, okay, actually, I shouldn't be calling it. We're gonna call it little n, which is what it's traditionally called. Z to the little n over little n. Okay, we're interested in this.
Good.
And we can take the expected value of log z, which is the quenched or annealed, anybody? Which one is this gonna be? Quenched, that's right. The expected value of log z is not equal, we can commute limits to absolute values because we're badasses like that. Limit n goes to 0 of the expected value of z to the n minus 1 over n. Right? So if we can do this this was all just combinatorics and chug. If we can do this for arbitrary n, and then of course we're used to n being an integer here, right? So if we can do this for arbitrary n, and then live with ourselves after sending this integer quantity to 0 in this ridiculous way, we can do that combination of things, then we can calculate the quenched free energy. Okay? And this is the replica trick. The replica trick is saying, let's have n replicas of the system, send n to 0, and get get quenched quantities from annealed quantities in that way. Okay? So there's a good reason why there's a thing called replica symmetry break. This is just what I was doing. Okay, this is just explaining the replica trick again. Okay, so I'm just going to give the super quick rundown now for what replica symmetry is and why it sometimes breaks. So it is often very, very useful as an intermediate step in these calculations to have what's called the overlap matrix. Okay, if we were doing, if we had time to go through all these calculations, you can see why now you're just gonna have to trust me, which I know Stuart does. So the overlap matrix QAB, where A and B are both indices from 1 to n, where n is of course equal to 0.1. The overlap matrix is a n by n matrix, which is in general some measure of the similarity between the state replica A and state replica B. So here, the only way two states can be similar is if they're identical, right? There's no other structure in the system, but usually it's something like 1 over n of the sum of sigma A I sigma B I, where I goes from 1 to n, right? So this is like sort of the dot product of the two configurations, right? And here, if this is equal to 1, then they're identical, and this is equal to anything other than 1, then they're completely different, right? Like that's so morally, that's what this overlap matrix is. And so we do some sort of saddle point approximation in the overlap matrix. Okay, so we're going to express our full partition function as some functional of the matrix, and then do a saddle point approximation in this matrix. And what we find is at really low temperatures, the matrices that show up in the saddle point approximation are not replica symmetric, right? They should have an Sn symmetry, right? The initial problem, if we have n replicas, has permutation symmetry among the n replicas. And you can really think of it almost as spontaneous symmetry breaking of that perturbation, of that permutation symmetry. That's what replica symmetry breaking is. Yeah.
So, I mean, if I permute the replicas in the partition function, there's just a sum over these dummy indices. So how does permuting those replications, those replicas, change any map?
That's the point. Yeah, it's still a symmetry. Replica symmetry breaking is spontaneous symmetry breaking. So it's still a symmetry, but the dominant contributions come from configurations that break them. So for instance, okay, so an example is, suppose we had three systems. There are going to be some configurations where, and it turns out these will never dominate for the p-spherical model, but whatever. They'll never dominate for the main dimension model. They might dominate for other models. There's going to be some systems where like replica 1 and replica 2 have a huge overlap, but they have a weak overlap with replica 3, right? And you can imagine those dominating.
So it's configuration specific.
Yeah. So replica symmetry breaking, is when the dominant contributions break replica symmetry, even though the overall problem will still have replica symmetry.
Okay.
And that's why I'm saying it's like spontaneous symmetry breaking, right?
Okay.
But what normal spontaneous symmetry breaking is like, if you have a magnet or whatever, the problem still has up-down symmetry, but the dominant configuration is either going to be all up or all down. Okay. And I promise this is related to ergodicity breaking in some way, but I think we're out of time.
Yeah. I think we're good. We're
Okay.
good up to 6.
Okay, yeah, so I don't, anyone have time for final questions that won't take too long? So if someone has something really good to end us out.
So, let me ask you like a quick question. So how does the spontaneous, say, replica symmetry breaking related to the universality or some other critical exponents, etc., etc.? Is there any?
So I mean, it is, so the replica symmetry breaking is an actual bona fide phase transition you can see in the free energy. So it should have some universality. Okay, now I'm starting to wonder, is it spontaneous symmetry breaking, could it have a Goldstone mode? I've never heard anyone talk about this. And it is a discrete symmetry, so maybe not. But it's also crazy and breaks all the rules, so maybe it does. Anyway, I'm sure it has a universality class. I admit I don't know what universality class replica symmetry breaking is here. I don't know.
Is there a replica charge
Replica. I mean, so yeah, it's not a U1 symmetry, so it's not charged in the conventional sense. It's an SN symmetry, so you can say a given state transforms in this representation of SN, right? But really, you should just be like say, hey, we have a configuration that transforms under permutation, and breaking it into irreducible representations, I think is just silly, but you do you.
Right, any more questions? Experimentalists or other theorists?
Are there non-trivial statistics? Are you referring to when they permute, if you get a different phase or something? Is there an analogy here?
What do you like?
So like a fermionic statistic?
Oh no, this is as far as I know, this is completely different from anions, any of that, right? I agree they both involve an SN symmetry. And they do actually sort of involve, okay, but now these things are distinguishable. I don't know. I don't think there's an analogy. I take back there definitely not being an analogy, but there might be something there. But I certainly don't see what the similarity is. Let's leave it at that. Yeah, they definitely both involve permutation symmetry. But it's sort of like, here, like they're identical systems, so in some sense they're indistinguishable, but they're in different microstates, so they kind of are distinguishable. Any other questions?
Does this have any experimental relation?
So ergodicity breaking obviously has experimental realizations. So you can just be like, hey, look at my thing, it's still where it was before.
Replica symmetry only applied to a spin glass. Is there any other?
I mean, so like replica symmetry, like you can use this technology for anything, right?
But
Like,
it only had phase transition. Phase transition.
yes. Yeah. And like this is a phase transition, right? So like you can go and if you could build a random energy model in a lab, you could go and cool it down. And like physically what will happen, I guess I didn't give this intuition here. Physically what's happening is for any realization of the random energy model, it's a ground state, right? So the what's it? Quenched or annealed, which one's the easy one? Annealed average, the energy is just proportional to beta. So as you raise beta, the energy is going to become more and more and more negative, and then you're going to hit the ground state, and there's a phase transition. That's physically what's going on. And that's obviously very detectable. If you could build this system in a lab, that would be very detectable in a lab. There are analogous systems. There are spin glasses you can have in a lab, and you would detect this phase transition in the lab. You, of course, wouldn't detect replica symmetry, because replicas are a mathematical trick. You don't build replicas in a lab, but you would detect the underlying phase transition, in the free energy in a lab. Okay, is that all the questions for now?
I think so.
Okay, great.
Thank our speaker, Mike, for the exciting talk. Right, let's stop the sharing